Treasure Valley data enthusiasts. This is Mike Migalski from Infovia, and happy to present to you today the May 2024 edition of Treasure Valley Data Enthusiasts. Thank you for joining. Our speaker today is a new friend of mine, Dave Hay. I've read his books. I've had his books for quite some time. Dave's written several of them on data modeling, including a more recent one called Achieving Buzzword Compliance, Data Architecture, Language, and Vocabulary. Dave and I met at a conference recently. I said, would you come to Boise and speak? And we agreed to do this virtually. So he's tuning in from Texas. And here we are in Boise. And without further ado, renowned author, Dave Hay. To you, Dave.
Good morning, or good afternoon, or good evening, depending on where you're sitting. Yes, this is in response to the folks in Boise, Idaho. I am sitting in Houston, Texas, as it happens, the wonders of modern technology. As he says, my name is David Hay. I founded a small company called Essential Strategies International some 40 years ago. I would like to introduce myself as being a bit older than pretty much everybody in the room, having been born the first half of the last century in 1947. This was in a small town about 500 miles southeast of Boise called Grand Junction in western Colorado. This was a bustling town of about 20,000 people that made it the largest municipality for 250 miles in any direction. Now, also born in 1947, many miles away, back east in Scranton, Pennsylvania, was a data modeling expert that you guys may know at Boise State named Mike Leinert. Also in 1947, born not anywhere near any of us in the United States, in Taiwan, a fellow named Peter Chen, and we're going to get to know him a little later. Now, so much for the important history. Minor thing that happened in 1947 back in New Jersey was the invention of the transistor. That was important to me when I was a kid because the transistor radio was handy and right in my hand, way different from what they call wireless, devices that were on the table. Now, it happens that 1947 was a good time for the transistor to be invented because a year earlier in 1946 was the electronic integrated numerical computer. That is the first major electronic computer was installed in Philadelphia, Pennsylvania. But it was all operated via vacuum tubes, which tended to get hot and tended to burn out, which means the whole thing wasn't as reliable as it might have been. And they were waiting for the transistor and its comparative components to go along with it. I mentioned that Grand Junction was kind of isolated. My knowledge of the outside world was pretty much limited to newspapers, magazines, the public library, and of course the odd James Bond movie. By 1965, I was about ready to go. When I was 18 years of age, I set out to seek my fortune. And the first time I was in an airplane, 3 hours later, I was by myself in the middle of Los Angeles International Airport at 5 o'clock on a Thursday afternoon, trying to find my way to college. Pretty much the rest of my life is spent recovering from that afternoon. Now, you should understand, if you're going to get introduced to this brand new world, which is the outside world, you can't be doing it in Southern California in the second half of the 1960s. Pretty much everything was falling apart at that time. It was all strange and wonderful. And I think 4 years later, I may have adjusted because the most obvious, reasonable thing to do in 1969 was to get married on Saturday, graduate on Sunday, and set out hitchhiking cross country to seek my fortune in New York City. Now, millions of people have been doing that, of course, over the years. It's perfectly reasonable to arrive with no money, no job, no experience, and a dream. And that's what I was doing. I did happen to have in my pocket a college degree, but that meant I was knowledgeable in the world of philosophy, which in 1969 was not nearly as useful as it could be. Interestingly enough, 20 years later, it was useful, but in 69, not so much. I did discover after 3 days of basically being lost, the secret to success. Okay, sure, there is talent. That's great. Hard work is very good, but you can't beat dumb luck and the kindness of strangers. And that was what I had. I was sitting in the coffee shop wondering what the hell was going to happen to me. And I met up this fellow who'd cracked up his Mercedes out on 49th Street, and he was in a bad mood. And we got to talking, and he discovered that deep in my college career, I had learned how to program for a wonderful language called Fortran. Ah, I can use you. It turns out he represented a company with a brand new technology called computer time sharing, which was a convoluted way of describing the fact that you could sit at a teletype machine and you could type in your program and see it in text on the teletype machine, press the button, and thanks to the wonders of Bob Bell, it would be zipped out to Long Island somewhere where it would be compiled and run, and the output would be zipped back to you at the teletype machine. Now you have to understand back in those days, the definition of zip was count them 100 bits per second, but it worked. And yes, it is true that I was in sales, which was an awful idea. I sorry, I was selling a technology that was understandable to anybody, including me, in the world of business, which was kind of alien in New York City. So you can't beat it. This is what they call the formula for a success. Well, it didn't feel like it for a while, but it was all right. And I struggled. And after a while, I wound up in a consulting company where I wound up helping people develop systems for market research in the wonderful world of Lever Brothers and General Foods. And finally, by 1975, I had acquired my graduate degree, my MBA. Again, a wonderful, useful major called um, quantitative analysis, which once again, 40 years later would be great. 1977, 75, less so. But I did get a great job with Pfizer Pharmaceuticals, and I got to get involved in a new world called manufacturing and inventory control systems. There was even an acronym for it, MRP, Material Requirements Planning. And this was a technology whereby the computer would take a set of sales forecasts for finished products out some weeks or months into the future, would process that with the structure of each of the finished products and come up with a corresponding forecast of the requirements for component parts or raw materials. Now, this is a cool piece of software, and the clients really appreciated it, and Pfizer really appreciated it. However, there were a lot of companies competing, and it was very clear straight on that the companies that were doing well were the ones that actually understood the nature of the underlying data. And the companies not so well didn't understand it so well. Okay, that was phenomenon number one. Phenomenon number two was that if you get down to these requirements for components and raw materials, you actually have to know how much stuff you have on hand of these things in order for anything, in order to do anything. Well, this is not a programming problem. This is a management problem. And it turns out that even back in 1975, it didn't have a name yet, but there were the makings of something called data management, which had two qualities. One is it was very important, and second was it's hard. Now, 50 years later, we've got people having titles being data manager and are trying to do this stuff, and they're discovering two very interesting things as though it's brand new. It's very important and it's hard. Times haven't changed a bit. Okay, meanwhile, over the 1970s, well, back in the 50s and 60s, that first computer that was built in 1946, over the 1950s, they had data in punch cards and magnetic tape and punch tape. And that was sort of clumsy to manage. But in about 1963 or 64, they came up with the direct access direct access storage device, otherwise known as the magnetic drum and the magnetic disk. And this meant that you could refer to data anywhere, randomly. You don't have to scrim through a tape or through a deck of cards. This was way cool. The programming that supported it was very complicated, however, and people were getting incredibly confused. Well, in 1971, a mathematician came up with what he called relational theory, which said that if you want to organize data, the intelligent way to do this is in simple tables. And the tables are defined by a set of columns, and you have a set of, and the rows are instances of the thing that the table is about. And you have simple tables with rows and columns, and then you have other tables that are related to those tables. And the thing is, you can define the relations in logical terms. You don't have to do programming stuff. Well, it did take about another 5 years for Oracle and other companies to come up with the programming part of it, which is to say they had what came to be known as relational database management systems, which did take advantage of the relational theory. Also in 1976, Peter Chin, remember him from 1947? He came up with a graphic way of representing these models, and he called them entity relationship models. We're going to learn more about that in a few minutes. Now, his drawings were basically boxes for what he called entity types, which is to say categories, and actually rhombus shaped, more boxes for the tables that connected tables to other tables together, which meant the relationships were named by nouns, which we'll talk about more about that in a minute, which were fine, and the attributes were hung off as in circles. This was a little clumsy, and the dear old U.S. federal government said, we got to do something better than that. So they came up with a notation for relational databases, which they called IDEF1X. Now, if you can imagine the federal government sending out to design an artistic way of representing something, you can imagine what that looked like. Well, there was a company that made good money in supporting that notation, but their customers were complaining about the fact that this is too complicated. Can I do something with the logic of the problem? Well, it so happened that in California, a fellow named James Martin and his colleague in Australia, of all places, had come up with a way of managing data called information engineering. And this has a whole lot of components, some of which are valuable even in the modern times, but included a way of representing this in diagrams. And this diagram was to be a lot more accessible than the IDFX diagram. And so the software company called this logical data models. And we're going to talk more about that. The problem with this notation is that they thought that these things were related in terms of verbs. So one of these guys acted upon the thing around it. We're going to talk more about that in a few minutes. Okay, in 1986, I went to work for Oracle Corporation, and there was this fellow there who said, if the Oracle database was kind of complicated for me, you should understand this thing called data modeling. And he showed me a way of doing it that was developed by a couple of Brits named Richard Barker and Harry Elf that were aesthetically way more accessible so that the average business person could read it and understand it. And secondly, with a discipline to the way things were named. And we're going to learn all about that discipline in a few minutes. What I did discover is that if I did a model for one client, and there were various departments in that client, and I did models for the various departments, and I go to another client, and there were the same kinds of models, same kind of departments in that client, many of these were the same models. I said, hey, there's something going on here. And so my first book in 1985 was called Data Model Patterns, Conventions of Thought. And this was a standard set of models for standard business situations. And it turns out that was the first time anybody had ever written that. Now, there were successors after that, among them being a fellow named Lem Silverstein. No, I'm sorry. Anyway, Lem Silverstein. And he wrote one that was similar, but in way more detail. And I didn't think it was as generic as it could have been. But I wrote some other models over the years, and by 2011, I was ready to have what I called the enterprise model patterns describing the world. And these were much more comprehensive, and they specifically represented different levels of abstraction. Level one being like the models in my first book, level two being more specific to departments, and level three being enterprise-wide, like the oil industry and the banking industry and so on. Now, you should also know that by 2011, I had been hanging out way too much with a group called the Object Management Group. These were guys who were not interested in commercial applications as much as applications that were object-oriented. And this became particularly popular in the days of video games because the objects were bits of code that behaved in certain ways. And the problem was that they came up with a way of modeling data, but it wasn't the same. And I was saying, no, no, that's wrong, that's wrong, that's wrong. And they said, no, it's not, it's just right. And finally, one day, the light bulb went off, and I said, I understand. You're not trying to do the same thing we're trying to do with a commercial model. Duh. But what I can do is I can take the notation, the physical, the graphic notation, and I can use it for my purposes for data modeling. And what that meant that first book was UML and data modeling and reconciliation, which is going to be the subject of today's presentation. But once I had figured out how to do it, I was able to use the same notation for my enterprise model patterns book. So today we're going to learn about this. Oh, I should also explain that in the interim years, I wrote a book on requirements analysis, which we're going to talk something about later, and about metadata, which we're not going to talk about at all. Now, okay, you have, and buzzword compliance, as Mike mentioned, this was my response to the data management field. We're happy as data consultants, happy to go into our clients and say, you guys have screwed up the way you use language. The same word means three different things. The same concept has 5 different words for it. You guys are confused. And, my colleagues and I have made pretty good money helping people with this. The only problem is our own field. Because in our own field, we have something called a conceptual data model, which means at least 3 different things. A logical data model, which means at least 4 or 5 things. What about a semantic data model? Or worse than this, there were others and others as well. So anyway, this is a book that attempts to address those. All right, so in the room we have people already who know some data modeling and people already who know some UML modeling. And the objective of today's presentation is to get you to talk to each other. Okay, the data modelers are 2 flavors. One is people who are modeling data so they can design databases. Wish this had a simple back. They're focused on, Oracle or DB2 databases. And then the business data modelers, like yours truly, they're more interested in semantics. Now, over here, we have UML modelers that are interested in object-oriented design, and there are other UML modelers with other ideas as well. Okay, now, unfortunately, I'm not in the room with you guys, so I'm going to make a guess that about half of you in the room have experience with data modeling, and half of you in the room will have experience with UML modeling. So we'll go from there. For those of you who have experience with data modeling, they're typically in 2 camps. And by the way, for our purposes, I'm going to use the term entity relationship modeling, or ER modelers, thanks to our friend, Mr. Chen. Specifically, there's the database designer's view, as I mentioned before. The problem is object-oriented design is different. UML is evil. And of course, for the semantic modeler's view, the problem is that UML doesn't focus on business. UML is evil. Well, there's a problem with that. UML, Unified Modeling Language, is here. Sorry, it's widely recognized as a standard. Clients and hiring managers want to know if you know UML. Well, after today, you will be able to say you do. But what is UML? It has several kinds of models. They're the ones they call class models, which are a lot like ER models, but the problem is it can be anything. First, it starts with an object. I mentioned it was object-oriented. Well, object is any discrete entity that has a well-defined boundary and identity that encapsulates state and behavior. So an object might be this video game critter that has a boundary and is in a state of being created and then disappearing and so on. It's an instance of a class. So what do you mean by class? Well, class obviously is a set of objects. Right? For those of you who may not be familiar with the linguistic term tautology, if you were to go to the dictionary and look up tautology, it would be defined as a noun, and the definition would be see tautology. Actually, that was my joke for a long time, and I was upset when a few years ago went into Merriam-Webster, and that was exactly the definition that was there. Although a year later, I looked and no, they don't have that definition anymore. Point is something being defined in its terms of itself. Now, this is not just a set of objects, but does share a set of the same attributes. It shares operations, things that it's related to, methods, and behavior. Okay, we're learning a little bit more about these things as we go along. Now, how are they related to entity classes or entity types, what we're going to call in a moment? Now, in UML, a class can be any kind of thing. It can be a business object. It can be, a class of computers or a class of people even. Or it can be a technology object, one of those critters on the video game. Or it can be any noun for that matter. If you are doing AI and studying a text, be any of the noun in that text. As far as UML is concerned, that's fine. An entity type, this is Peter Shen's term, is a subset of the UML concept of class. Specifically, it's only those classes that are of things of significance to the business. Okay, what is UML? As I say, it began in support of object-oriented design. It's not a single notation. It's an array of technical notations for classes and associations, activities, class behaviors, states and events, and other things. Okay. It can be done. We can use it for our data modeling problems. Okay, it's extensive, but we can take a subset. It has some quirks, but you're going to learn how to get around them. It is, well, how can I say this? Not beautiful. Sorry, but you're stuck. There are some things we can do. Premise. The entity relationship model is not the same thing as a class model in UML. However, it is valuable to learn new ways to do things. You can learn to improve your modeling no matter what notation you use. Okay, that's for the data modelers. For the UML modelers, you should know that we're only concerned with entity classes that pertain to the business at hand. There's only going to be a notation of the subset that you know in UML. The UML class is analogous to the ER model entity class for business things only. Now, in UML, what you know as a role is analogous to the ER relationship end, but that is an assertion about the nature of the relationship. It's not about the behavior of the relationship. Now, an attribute in ER is about the same as the attribute in UML. Language is used differently. In ER, it's normal entity class, normal English entity class and attribute names including spaces between words. The role in ER modeling is a business assertion. It's not the label for another entity class. Okay, this is going to be a little weird, and you'll have to see that in just a few minutes. In ER, the relationship is about the structure of these things. Remember, these are business things, business objects, and they're related to each other. They are not behave in certain ways around each other. Okay, modeling for analysis, systems analysis. You probably have heard of systems analysis. You should understood we've been doing systems analysis for at least 20 years before UML came along. UML happened in about 1999. In my and anti-relationship modeling, as I mentioned, Peter Shin came up with 76. Now, when I started at Pfizer, my first assignment was in the plant that made pharmaceuticals. And it started with a work order that was sent out from headquarters. And the plant manager looked at it, marked up the work order, gave it to the first foreman, who marked it up, gave it to the next foreman, and so on and so forth. And it turned out that by the end of the process, in order to get a single lot of the pharmaceutical, you need at least 12 copies of the work order. This seemed to me not a good way to represent it. And I didn't have a modeling approach at the time, and so I kind of had to make it up. There were IBM had something called flowcharts, but that wasn't really good because that was about IBM equipment. So I kind of faked it and came up with a way that sort of worked, but it really wasn't quite right. And in 1979, Trish Sarson and Chris Gain came up with a book called Structured Systems Analysis Tools and Techniques. And this was brilliant. They recognize that you start with a description of how the data flows in terms of technology, the work order forms and so on. It might be in forms of being spit out by a computer, like computer reports. And then they said you figure out what all of these physical flows are, and then you convert them to what they call logical flows. Now, the method of going from a physical flow to a logical flow was a little iffy. And so their buddies, Steve McMenamin and John Palmer, said, what you need is something called essential systems analysis, which was basically saying that you take the physical steps, the steps that are described physically, and you break these into small pieces, and then you look at the external entities, the sources and destination of each of these entity elements, and take the source, and what is an essential source? Okay, you receive an order, or you issue a shop order. Okay, what are the steps that are the response of that? You take these steps, draw a ribbon around them. Each of these is an essential process. And from there, you have a nice, elegant, what they call an essential data flow diagram. And I like the word essential and adopted it for my company. Now, modeling for analysis is all about the business space, whether it's what are the things in the business, how are they related to each other, how does data flow from one to the other. This is what's called the problem space. It's not about the technology, which is the solution space. Now, some of you have out there a book on your shelf called Object-Oriented Systems Analysis. This is false. This is a fake. There is systems analysis, which is identify the problems in the business. And if you've done that, then what are you going to do to solve those problems? There are lots of technologies available to solve the problems. They might be object-oriented programming. It might be build a relational database and do something with it. It might be COBOL for you old timers. Point is, there are many technologies that are available. There are probably a limited number of elements to the nature of the business. A class model in UML is not the same thing as an entity relationship model. However, it is valuable to learn new ways to do things. You can learn to improve your modeling no matter what notation you use. Note, there are better and worse data modelers. It's true. Some people do this really well, some not so well. Well, there are better or worse UML modelers, and it's the same story. Well, by the way, neither of these communities is what you would call homogeneous. It's the collection of you guys that I'm talking to today, and we're going to try to come up with some ways of, well, what the objective today is to provide all modelers guidance to producing an excellent entity relationship diagram. It happens to make use of the UML class notation. Okay, that, after half an hour, is our assignment. Today's work, based on my book, published in 2011, based on work that I've done with the object management work group, along with the three amigos that we quoted before. I used this version of UML in a companion book, Enterprise Model Patterns. When I told my colleagues in the data modeling world that I was going to use UML for this book, they were horrified. When I told my folks at the object management group that I was going to use UML for this book, a modified version of UML, I said, you can't bastardize UML. Well, I did. So both populations were sort of unhappy. Both have later decided maybe I knew something. Okay, elements of great model. We've got several subjects here. First is the notation itself. Second is the use of language, how they approach supertypes and subtypes. Domains are, if you have an attribute, what is its range of values? You know, UML for the longest time had a weird way of identifying each object, which was limited, and a lot of people argued against it. And finally, they modified UML a few years ago, so it actually does address it better. And then finally, aesthetics. And aesthetics, by the way, is something the data modelers have as much problem with as UML modelers. And I want to come down hard on both. So starting with notation, entity types and classes, and then relationships and associations, entity types and classes. Okay, an entity is something of significance about which you want to hold information. This computer is an entity, this room is an entity, I am an entity. This is something of significance about which you need information. An entity type is the class of those things. So this class of things that we're going to draw pictures of. All right. So here we have a set of entity types. And each one is named. And each one has a set of attributes. So for example, vendor is defined as a person or organization that wants to sell us something. An attribute, on the other hand, is that information that you want to hold. In this case, you'll have a vendor ID, vendor name, and a street address. Now note that we have some boxes inside other boxes. Think of this as a Venn diagram for you old symbolic logic guys, and it's exactly the same thing. A subset is a set of instances that are subtypes of the supertype. So for example, here you have something called a geographic area. The definition of a geographic area is an area on the earth that has a boundary, has a recognized boundary. Okay, it's geographic, it's geo because it's on the earth. Yes, the same thing could be extended to the solar system, but we're not going to go there. What you do have is a subtype called a city, which is defined as a geographic area where the boundary is defined by the state. So for example, the city of Boise is a geographic area whose boundary is defined by the state of Idaho. The state of Idaho, on the other hand, is a geographic area whose boundary was defined by the United States. And the United States, on the other hand, which is a geographic area whose boundaries were established by a series of treaties. All right. An entity type is defined in the singular for a representative entity. So you talk about the entity type is a person or a product type. It is not project history. History is a collection of instances of projects. So the thing itself is a project. So this is how we're identifying entity type. Employee table. Whoops, table? That sounds like a database. That doesn't sound like a thing in the business, and that's true. It's not. What you were probably thinking of, and this is wrong, is employee. Now, and this is the starting point for everybody who does a data model. And everybody who does an data model has to fix it because employee is not a thing of significance. The thing of significance is a person. The thing of significance is a collection of persons called an organization. Now, a person gets to be a certain age and gets a job. When a person gets that job, that is an employment of the person in an organization. So in each case, what is the thing of significance? This is not an easy thing to come by. We're going to talk more about that in a moment. Zip code comes up a lot in your models. Well, zip code is an attribute. It's a number that identifies a geographic area, which happens to be called a postal area in the UK or in Canada and other parts of the world. And it's not called a zip code in Canada, it's called a postal code or a postal area code, better than that. So be sure you understand which things you're talking about. An entity type is a set of entities described by a set of attributes. Okay, entity types and classes. When the UML people came along, they claimed that it was superior because data modelers don't understand the difference between objects and classes. Wrong. UML object corresponds exactly to a data model entity, and a class corresponds to a data model entity type. Now, the problem was the data modelers would draw their boxes and would say, this is an entity because they're too lazy to say entity types. And so they got zapped by the UML people. And so from now on, we're going to not talk about entity type, we're going to talk about entity class, just to keep everybody happy. Attributes is a characteristic of an entity type that serves to quantify how many, qualify what color, identify which is it, classify what category is it in, or express the state of that entity type. But again, it's a simple English name, including spaces. Product code, product name, part color, so on. One may choose not to display the attributes, that's fine. If you do, you at least have to display the name and whether it's optional or not. If you want, you can also display its data type. More than that, you're clogging up the drawing way too much. Now, relationships and associations. Okay, on this model, we have lines, and each line is described with a bit of text. Now, each of these are assertions about the nature of the relationship between one and the other. So there's a relationship of purchase order to vendor and the relationship of vendor to purchase order. Now, these are rules, the very strict rules, linguistic rules for forming and naming relationships. Now, if you look at any other notation that has preceded this, in information engineering, IDEF1X, even in Peter Chen's version, you don't have the rules for the relationships that we have here. And this is what makes this a much more powerful notation than hang around. Each name produces a strong sentence. Now, your subject matter experts don't have to be able to read the sentence. But as a modeler, you have to produce these sentences from the drawing. For example, each sales order may be composed of one or more SO line items, each of which must be to sell one and only one product type. Now, is this a true statement? Okay, your subject matter expert should know. Can you have a sales order that doesn't have line items? Well, it depends on the company. Maybe some of you know. You can sell only one product type on a sales order. But what if I wanted to sell services? Well, in that case, you have to fix the language to cover that. Now, you may realize that this sentence comes directly from the drawing. Each sales order may be, because it's a dash line, composed of, and because there's a crow's foot line signal here, one or more SO line items. Each of which must be, because it's a solid line, to sell because there's no other symbol down here, one and only one product type. And that is exactly the sentences that we have down here. But I'll chew on that a moment. Now, there is a very powerful syntax for reading the relationships. Each first entity type must be, if it's a solid line, or may be if it's a dashed line, composed of, and the relationship name, and we'll talk about the nature of the relationship name in a moment, one and only one if there's no symbol here, or one or more if there is a symbol there, and the second line entity type. Okay? For example, each order, it must be solid line 2, and there's no symbol here, one and only one party. Each order must be to one and only one party. Each party, on the other hand, may be the seller in one or more orders. Each order must be from one and only one party, and each party may be customer in one or more orders. Okay, these are simple numbers that are meaningful to the subject matter expert. Note that the truth of these statements is in their hands, not the data model. If the subject matter expert says, no, that's not true, we can have an order that's to one or more parties, not just one, or we can have an order that's from one or more customers, not just one. Well, so we may have to fix the drawing because we may have to fix the language here. Okay, the role is part of an assertion about the universe of discourse. Its form is subject entity class, predicate object entity class. Now, you may recognize the structure, by the way, if you have any knowledge of semantic data modeling, because they have exactly the same thing in their triples: subject, predicate, object. In UML, on the other hand, it's the name of what an entity class means to the other entity class. Okay, this is kind of weird because the difference between the two is behavior. UML addresses it, ER modeling does not. Object-oriented design bundles with each class program code that creates, manipulates, or destroys instances of that class. Okay, this is way too much programming if you're interested in data structure. In the definition of the class of UML, we have definition of behaviors of that class. Behavior is not appropriate in your modeling. The only verb we're concerned with is to be, as in must be or may be. The content of the predicate must be a preposition. Okay, for you linguistic experts here, you recognize that you don't have to have a PhD in linguistics to represent that that's a part of speech. When did we have that? Back in grade school? Now, if you watch Sesame Street, Grover had action words like jumps, swings, hides behind. These were action words. Relationship words were over, under, around, and so on. These were prepositions. Okay. Remember the word rule of preposition isn't something you should end a sentence with? Well, that was a joke. You can't end a sentence with a preposition. Okay, UML, on the other hand, has something called namespaces, just to make life interesting. Now, this you should understand comes from their object-oriented programming world. In object-oriented designs, you may redefine and use names. Within a namespace, each name has a unique meaning. Named elements are declared in a namespace, and the names have a scope within it. Okay, this means in UML, each order is from exactly one something. Each order is to exactly one something. Note the related class may not be part of the source class's namespace. Now down here you have a party is a customer in 0 or more something. Party is in a vendor in 0 or more something. Now here you're saying something plays the role of being a customer for one order. Okay, this is their way of dealing with the fact that you would like to know what is this thing out here. So the role is what defines it. So something plays the role of being a vendor for one order. Okay, here you have something plays the role of being a purchase order for 0 or more parties, and then something plays the role of being a sales order for one or more parties. Okay, here you have an ER model. Okay, each entity may be contained in one or more subject areas. Each subject area may be a container of one or more entities. Okay, you'll note contained in subject area is the predicate for entity. So entity has contained in the subject area, and subject area has container in also. But this isn't allowed in UML. All you have to say is that each entity, this entity here, is 0 or more containing subject areas. Now note that containing subject area is a property of entity. Okay. But subject area itself cannot be part of that property. So it's not even allowed to see that. What you get is redundancy. Okay, similarly, each subject area may be 0 or more contained entities. Contained entity is a property of subject area. But entity itself cannot be part of that property. Okay, what if we play games here? Let's do a little Barker-Ellis language and with the UML notation. What do we get? Okay, each order must be from one and only one party. Ta-da! Each party, on the other hand, may be a customer in one or more orders. Ta-da! Each customer, each order must be to one and only one party. Each party may be a vendor in one or more orders. Now, you may know with familiarity that these are exactly the same words that we saw in the last model, but we're using the UML notation to capture it. Note the truth of each statement is the subject matter experts, not the data model. So UML roles can be named thus. Each entity class 1 must be if the second entity class has a 1 dot dot next to it, or maybe the second entity class has a 0 dot dot next to it. Role name, one or more. Second entity class has a 0 dot dot, has a dot dot star next to it. Exactly one has a dot dot 1 next to it, and entity class 2. So these can mean exactly the same thing. Each order may be composed of one or more line items. Each order may be composed of one or more line items. Or alternately, each order may be composed of one or more line items. Each line item must be part of one and only one order. And each line item must be part of one and only one order. Note that the optionality is at the subject end in an ER model, but in UML it's at the object end. So these two are equivalent statements, but you're moving it at the other end. So by convention, if you want to not get silly, crazy, if you work with both notations, everything gets read clockwise. So if you read everything clockwise, then you're okay. Now, are these optional? Are these attributes optional or not? In the case of the ER model, an attribute is mandatory if it has a star or a hashtag. Talk about hashtag in a moment. In the UML model, it's required if it has a 1, which is shorthand for 1 dot dot 1. And these are exactly the same notions for optionality and the relationship names. Note this is the unique identifier, and we'll talk about that in a moment. Now, the attribute may be optional if it's 0 here. Now, in the case of UML, it's 0 dot dot 1. Now, the dot dot 1 has to do with the fact that this is actually a relational model. And in the relational world, you can never have a multi-valued attribute. Line item must be one and only one delivery date. It might be not have any delivery date, but it must at least be one. Yes, we know. In UML, there are separate symbols being composed of. Often UML models are not labeled, so this is useful. UML models are always labeled, so it says part of, composed of, and part of. Symbols do represent 2/3 of what's called the referential integrity constraints. The first means delete cascade. If you delete the whole thing, you're going to delete everything. Or the second means delete nullify. If you delete the whole, you're going to delete parts, but they're unconnected. Sometimes useful to show them, but there is no such thing as deletion. It's not good. So this guy goes, bye. Role names are important. For those of you aware of this, the Hitchhiker's Guide to the Galaxy got sued because it published the following. Ravenous bug-blister beasts often make a very good meal for visiting tourists. That's great. I want to go to that planet because it's got stuff to eat. Well, that was a mistake. It was a typo. It was supposed to say ravenous bug-blister beasts often make a very good meal of visiting tourists. This is not the same thing at all. Language is important. The model is a graphic portrayal of assertions about the nature of the business. Feedback sessions, it is the English sentences that are validated, not the drawing. As my friend Mr. Lynott said, the purpose of a feedback session is not to be patted on the head about how pretty your drawing is, it is to be wrong. Now, the right sentences seem self-evident. If you got a whiz bang here and a doohickey over here, and there's a related, if you understand what a whiz bang really is, and you understand what a doohickey really is, and you understand the meaning of the word in between, then that should be self-evident. Or truly true or untrue. Getting those sentences right, on the other hand, is hard. I think great literature is a pleasure, or at least interesting to read. Great literature is very difficult to write. Note, while IT information technology education is useful for some of you, education in literature, history, philosophy, which is to say, knowing how to use your language, can be even more important to value. Now, this is true of English. It's also true of Spanish, of French, of Polish, even of Chinese and Japanese, by the way, which are more difficult. But the same issue is the same. Colors. This is to those of you, with all the respects to my colleague, Steve Hoberman, who've been learning information engineering, and it's all about verbs. Relationship names are not verbs. They describe the structure of the relationship between two things. Think of a bridge. You've got a bridge with this end and a bridge with that end. If you're not from Baltimore, you don't have a bridge that doesn't have connection between the two. Not about how one thing interacts with the other. That's object-oriented behavior. Here, for example, Mr. Hoberman's book, you have that each student, and this, by the way, is information engineering notation. This symbol means maybe, initially maybe, and eventually must be one or more. This is must be one and only one. So each student maybe initially must be eventually attendance in an attendance. Each class contains is contained in one or more attendances. Well, this is hard to understand because the student attends the attendance, the class is contained in attendance. Something doesn't work here. What you need is each attendance is by definition must have one student, and by definition it must be one class. That's the definition of attendance. A student, on the other hand, may be a participant in, or and the class, on the other hand, may be composed of or more attendances. But the bar there says, but eventually you have to have at least one attendance in a class. A student, by definition, at least must attend one class. Okay? Note that the preposition is way more disciplined than the verbs. Super and subtypes. We mentioned each person is a party, each organization is a party. By definition, instances of a party. By definition, the internal organization is a definition of organization. And the Marcalis schools recognize if you put one inside the other, that's what it means. Well, UML, inheritance is just another kind of relationship. So internal organizations inherit attributes from organization. Organization inherits attributes from party. Okay, there are symbols here for that purpose. So if you are clever and you recognize those symbols, then you understand this is what that means. But it's not nearly as intuitive as it is when you put the box inside boxes. Now, the case tool that I used didn't recognize the entrance, but I was able to add the lines, and graphically it does the same things. Now, some of you will say, but I want to have these things inherited by not more than one party. A person may not be, it'll be a party, but it may also be a machine. An internal organization may not only be an organization, but it may be a part of the computer as well. Okay, but the point is that Barker and Harris went back a little further in time to represent things here. Now, our friend Aristotle wasn't very good in sciences. His understanding of astronomy and physics left a lot to be desired, and he corrupted those sciences for a long, long time. But his knowledge of language and logic was spot on. And he understood that if you're defining a term, you first of all have to say, what category is that term? Okay, for example, an automobile is defined as a kind of vehicle. What makes it different from all other terms? Now, the Latin came along in the Middle Ages, differentia. That is, this automobile is a kind of vehicle that is used to carry passengers over land. It is not used to carry freight, and it's not used to carry it over water or through the air. That's the definition of an automobile. The point is that each of these definitions is in terms of its supertype. So the city, as they say, is a geographic area of that. A state is a geographic area of that. Country is a geographic area of that, and so on. Like domains. In the ER world, and each attribute has a data type. It's either numeric, a data, string, etc. It's also possible to define a category for a set of attributes called a domain, which could either be the data type, it could be a list of values, a numeric range, edit rules, mathematical expression, and so on. UML does not have domains in that term. It does, however, have a data type which is extensible to cover much the same territory. So, for example, if an entity class has a domain, specifically the code as a domain, each organization must be an example of an organization type. So if you have that, the example of a type, well, you have attributes for the type, which means that basically over here, you separately have to describe, well, what do you mean by that? Department, division, section, and so on. And this documentation is outside the model. Do that. Well, the UML folks came up with something that's very nice called an enumeration class. So this is a domain where the list of values is itself a property of the class. So internal organization has something called internal organization type, which is an enumeration. An internal organization type is in here with a list of values. There. This is very clever and something we can borrow. Unnecessary and missing from UML. Okay, relational design is based on uniquely identifying each instance. In ERD, a unique identifier may be an attribute. Each order number, for example, uniquely identifies an order. Or it may be a combination of the entity type as well as a relationship. So line number is line number one in the line item is only unique in the context of an order. So this is the line item is part of the unique identifier, and this relationship is part of the unique identifier. The UML doesn't have that. Basically, an object identifier is any object can be identified and referenced by any other object. Addresses or keys may be part of the underlying implementation infrastructure, but might be explicitly described. So, for example, that line number would be line number 7,225, because that's the unique identifier of that line number. That's not really useful if you're in the relational world. And they recognized this and said, so we're going to do something like an ID. The ID is a little thing that you can put next to the attribute, just like we had the hashtag for the attribute. Aesthetics. Okay, this is wrong. My credit to Peter Aiken to give me this wonderful example of a bad example. My problem is that I've had clients that required me to do that. These clients were fortunately, I had junior people who actually do the work, but which meant that a 2-month project now became a 1 year or 1.5 year project, just so that my client could have something he put on his wall. He impressed his fellow vice presidents. Say, see, I have a data model. Oh, yeah, well, what does it mean? What is the meaning of this relationship line that goes from here to there? That's not good. Well, it turns back again in 1976, in 1956 rather. George Miller, a psychologist, came up with the magical number 7 plus or minus 2, which was recognizing that the human brain is only able to hold about 7 plus or minus 2 things in your head, which means back in the old days when an area code was meaningful, you could hold a 7-digit phone number plus an area code, because my phone was the entire state of Colorado was area 303, and the entire city of New York was 212, so I could hold the area code. It's just another blob. But then they ran out of area codes, and so they didn't have that rule. So you can have the second digit can be anything, and the phone number of the second digit can be anything. So now suddenly you had to remember a 10-digit phone number. Ah, that's harder. So suddenly you had to have a cell phone that had the phones included. So you didn't have to remember your name, which is why to this day, if you're in the younger group, you don't actually remember your friend's phone number. Okay, bent lines are bad. Unfortunately, here you have only 7 boxes, but you have, for example, that, okay, a sample may be subjected to 1 test. Measurement may be for 1 test, or must be for 1 test, or it may be that this measurement is a collector of 1 sample. Or maybe it's collected by a person. Well, this is a bad idea. So get rid of the best lines. Make sure that every line is between just 2 entities. This makes it a lot simpler. Yes, you have 2 cross lines, but you know that this measurement is taken from a test. Test is the source of measurement. You know that the person is the collector of a sample, collected by a person. This is much easier. And then we'll take it another step and say, let's group all of the many bys off in the upper left. What this means is that up in this area, you have the transactions. This is the stuff that is done, behavior, if you like. And down here, you have what are the things that they're acting on? They're acting on people and samples, and their test types and variables, or they're part of the definition. And these things, as often as not, have dates associated with them, unless it's an expected thing that doesn't have a date. Now you can know that this is about clinical research. A person came in with got a blood sample taken, and a test was given on it. Now, this was a particular test type, and because it had particular test types, these variables were expected to be collected, and so this measurement was of these predicted variables. Summarize. Language is important. Daddy missed his slate, but I can't remember whether he said he was hung up with a layer over or laid up with a hangover. You have 3 symbols. In information engineering, these are the symbols. You have initially, maybe, and eventually must be one or more. You have must be one and only one. Unified modeling language is zero or more. You have is one or one and only one. Parker Ellis, you have maybe one or more, must be one and only one. Right, so those are the symbols of the three notations. Language is a little different. And information engineering is verbs, student attends and attendance. Means there's a redundancy there. Unified modeling language, roles. Subject area is one or more contained entities of an entity. Each entity is containing subject area of a subject area. Okay, so this is hiding this. This is hiding this. Parker Ellis, this is prepositions. By definition, each line item must be composed of one order. Each order may be composed of one or more line items. So there you have it. Where to buy? Technics Publications is my publisher. If you go to the technicspublication.com website, you can get UML and data modeling, and you can get that book. Or you can get Enterprise Model Patterns, and you get that book. Or you can get Achieving Buzzwords, and you can get that book. Better than that, if you're at their website and not on Amazon, you can enter a criterion that says, by the way, you know Dave Hay, and this is supposed to be get a discount for Dave Hay 30. You get 30% off on each one of those. Okay. Have we any questions? Mike, have you a question? If not,
Dave,
I would like to.
I think you almost
Okay.
filled up my 7 plus or minus, not plus or minus 2 spaces in my brain.
That's possible. That's entirely possible. So let me stop sharing for a moment.
Oh, I can take care of that.
No, I just, but I want to have my face show.
Okay.
So okay, this, so, and no, don't come, and my
There you
face to
are.
show up. Hey, okay, but I want to, can I be the full thing? Okay. How do I show us on my whole screen? Camera. There we go. Now, are you saying my whole big camera?
Yep.
If
I
you come
gotcha.
into a company and the data looks something like this, and your client is the first one to tell you that, man, that's so confusing. I'm not even sure I can understand it. I've been working here for years. And you say, well, that's true. But if you look under the surface, you'll find that there are structures there. And if you work with the structure, you'll come up with something that can really fly. And there you have it.
A magician on top of it all.
Yeah, something like that. So end of recording.
Thank you again, Dave. And
Well, you're more than welcome. I made it for an hour and 15 minutes. That wasn't too bad.
Appreciate your history lesson as well as your insights there. So today's recording will be published on YouTube. For future topics, you can email TVDE, Treasure Validated Enthusiasts, at infovia.com. And we plan on St. Luke's data governance journey. That says June. It's actually coming up next week in July, I mean. And we're looking for other topics. So please drop us a line if you have them. With that, that concludes our segment this month for the Treasure Validated Enthusiasts. Thank you for joining us. Bye-bye.